An eigenvector, also known as a characteristic vector, retains its direction when subjected to a linear transformation, albeit possibly with a scaling factor applied to it. This scaling factor, referred to as the eigenvalue or characteristic root, determines the amount by which the eigenvector is stretched or shrunk. Geometrically, vectors represent multidimensional quantities with both magnitude and direction, often visualized as arrows. When a linear transformation is applied, it can rotate, stretch, or shear the vectors it acts upon. Eigenvectors of a linear transformation are those that undergo mere stretching or shrinking, without rotation or shear. The eigenvalue associated with an eigenvector indicates the degree of stretching or shrinking, with a negative eigenvalue signifying a reversal in direction. In various fields such as geology and quantum mechanics, eigenvectors and eigenvalues are pivotal in characterizing linear transformations. Particularly in systems where the output feeds back as input, the largest eigenvalue holds significant importance as it dictates the system's long-term behavior following numerous transformations, with the corresponding eigenvector representing the system's steady state. In an n by n matrix A and a non-zero vector V with a length of n, when the matrix A is multiplied by the vector V and results in a scaled version of vector V by a scalar amount lambda, vector V is called an eigenvector of matrix A, and lambda is called the corresponding eigenvalue. This relationship can be expressed as matrix a times vector VV equals lambda times vector V. In an n-dimensional vector space with a chosen basis, there is a direct relationship between linear transformations within that space and n by n square matrices. As a result, defining eigenvalues and eigenvectors in a finite-dimensional vector space can be done in equivalent terms by using the language of linear transformations or the language of matrices. Eigenvalues and eigenvectors play a significant role in the analysis of linear transformations, deriving their name from the German term eigen, which translates to own or proper. Initially applied to investigate the principal axes of rotational movements in rigid bodies, these mathematical concepts find widespread utility in various fields, such as stability analysis, vibration analysis, atomic structures, facial recognition, and matrix operations. An eigenvector, denoted as V of a linear transformation T, is a non-zero vector that does not change its direction when transformed by T. This transformation, applied to the eigenvector, results in the eigenvector being scaled by a number called lambda, which is known as the eigenvalue. This relationship is expressed by the equation T of V equals lambda times V, referred to as the eigenvalue equation. Notably, lambda can be any scalar value, including negative numbers, zero, or complex numbers, with each case affecting the eigenvector differently during the scaling process. An illustration centered around the Mona Lisa portrays a simplified depiction of a linear transformation known as a shear mapping. This transformation causes points in the top half to shift rightwards, while points in the bottom half move towards the left, their displacement relative to the central horizontal axis, dictating the extent of the shift. Consequently, vectors emanating from the painting's midpoint to individual points become slanted either left or right, and are elongated or shortened by the transformation. Notably, points situated on the horizontal axis remain stationary post-transformation. Eigenvectors of this mapping, which are vectors devoid of any vertical component pointing solely left or right, retain their direction unchanged and possess an eigenvalue of 1 since their length remains unaltered. Linear transformations manifest in diverse forms across various vector spaces, thereby resulting in a multitude of eigenvector representations. In one scenario, a linear transformation may manifest as a differential operator, yielding eigenfunctions scaled by the said operator. Conversely, if the transformation is presented as an n by n matrix, its corresponding eigenvectors take the form of n by 1 matrices. Utilizing eigenvalues and eigenvectors facilitates matrix decomposition, such as diagonalization. These mathematical entities give rise to interconnected concepts, with the prefix eigen commonly used in their nomenclature. When discussing a linear transformation, the amalgamation of all eigenvectors paired with their respective eigenvalues is termed the eigensystem. Furthermore, a collection of eigenvectors corresponding to a common eigenvalue alongside the zero vector constitutes an eigenspace or characteristic space linked to that specific eigenvalue. Should a group of eigenvectors of a transformation T establish a basis for T's domain, this set is identified as an eigenbasis. Leonhard Euler's examination of the rotational dynamics of rigid bodies in the 18th century led him to identify the significance of principal axes. Joseph Louis Lagrange later connected principal axes to eigenvectors of inertia matrices. In the early 19th century, Augustin Louis Cauchy expanded these concepts to classify quadric surfaces and generalized them to higher dimensions, coining the term racine characteristique, characteristic root, for what is now known as an eigenvalue. Joseph Fourier leveraged Lagrange and Pierre-Simon Laplace's work to solve the heat equation using variable separation in his 1822 treatise. Charles-François Sturm further developed Fourier's ideas and introduced the relationship between real symmetric matrices and real eigenvalues, later extended by Charles Hermite to Hermitian matrices. Francesco Brioschi and Alfred Klebsch made advancements regarding the eigenvalues of orthogonal and skew-symmetric matrices, respectively. Karl Weierstrass highlighted the destabilizing nature of defective matrices in the stability theory pioneered by Laplace. Joseph Liouville's work on eigenvalue problems led to the establishment of Sturm-Liouville theory. Schwarz and Poincaré explored eigenvalues of differential equations towards the end of the 19th century. David Hilbert delved into integral operator eigenvalues, introducing the term eigen in German to signify own in 1904. The shift from the prior term proper value to eigenvalue occurred over time. The first numerical method for computing eigenvalues and eigenvectors, the power method, was formulated by Richard von Mises in 1929. The widely used QR algorithm, devised by John G.F. Francis and Vera Kublanovskaya independently in 1961, remains popular today. Eigenvalues and eigenvectors are crucial in linear algebra, especially when dealing with matrices. These concepts help us understand how linear transformations work within finite-dimensional vector spaces, which are often represented by matrices, particularly in numerical and computational applications. When a matrix, which we will call A, acts on a vector x, it stretches or compresses the vector, but does not change its direction. This makes x an eigenvector of A. To illustrate, let's consider two n-dimensional vectors represented as arrays of scalars. Vector x equals open bracket 1, negative 3, 4 close bracket, and vector y equals open bracket negative 20, 60, negative 80 close bracket. These vectors are scalar multiples of each other, meaning they are parallel or collinear. This relationship is evident if one vector is a scaled version of the other, expressed as x equals lambda times y. In this case, lambda is equal to negative 1/20. When considering a linear transformation applied to n-dimensional vectors, this transformation can be defined by an n by n matrix, referred to as matrix A. When matrix A operates on a vector v, it produces a new vector, denoted as w. This relationship is expressed as a times v equals w. If it so happens that the resulting vector w is a scalar multiple of the original vector v, this is expressed as a times v equals w, which also equals lambda times v. Here v is known as an eigenvector of the linear transformation represented by matrix A, and lambda is the eigenvalue associated with this specific eigenvector. The formal representation of the eigenvalue equation for matrix A is given by the expression a minus lambda times I times v equals the zero vector. In this expression, I denotes the identity matrix with dimensions n by n, and the zero vector is the vector with all elements equal to 0. A second equation shows that there is a non-trivial solution v when the determinant of the matrix, a minus lambda times I, equals 0. This defines the eigenvalues of matrix A as the roots of the equation. Determinant of a minus lambda times I is equal to 0. Using the Leibniz formula for determinants, this leads to a polynomial function in equation 3. The degree of this polynomial is n, which is the size of matrix A. The coefficients depend on the entries of the matrix, but always end with -1, raised to the power of n times, lambda raised to the power of n as the term with the highest degree. This polynomial is called the characteristic polynomial of A. This equation is known as the characteristic equation or secular equation of A. According to the fundamental theorem of algebra, this can be factored into n linear terms. It can be expressed as determinant of a minus lambda times I is equal to lambda 1 minus lambda times lambda 2 minus lambda, and so on up to lambda n minus lambda, where the lambdas can be real or complex numbers, and these are the eigenvalues of A. These eigenvalues, which may not all be distinct, represent the roots of the polynomial. For example, consider the matrix A with values 2, 1 in the first row, and 1, 2 in the second row. To find the determinant of the matrix, A minus lambda times the identity matrix, calculate the determinant of the 2 by 2 matrix with entries 2 minus lambda, 1 in the first row, and 1, 2 minus lambda in the second row. The characteristic polynomial is given by 3 minus 4 times lambda plus lambda squared. Solving this characteristic polynomial gives roots at lambda equals 1 and lambda equals 3, identifying them as the eigenvalues of matrix A. To find the corresponding eigenvectors, solve the equation A minus lambda times the identity matrix times B equals 0. The eigenvector for lambda equals 1 is the vector with entries 1 and negative 1, and the eigenvector for lambda equals 3 is the vector with entries 1 and 1. When the entries of matrix A are real numbers, the coefficients of the characteristic polynomial are also real, but the eigenvalues can have non-zero imaginary parts, which is reflected in the eigenvectors. Furthermore, eigenvalues might be irrational even with rational or integer entries in A, though they must be algebraic if A's entries are algebraic. Real polynomials with real coefficients showcasing non-real roots will exhibit complex conjugate pairs, characterized by having similar real parts with differing signs in the imaginary components. Matrices of odd order guarantee at least one real eigenvalue, while even ordered matrices may lack real eigenvalues, presenting complex conjugate eigenvectors associated with complex eigenvalues. The spectrum of a matrix is essentially the set of its eigenvalues, accounting for how frequently each appears according to their multiplicities. An important notion related to the spectrum is the spectral radius of the matrix, which is the maximum of the absolute values of all its eigenvalues. When you have an eigenvalue, say lambda sub I, of a matrix A that is n by n, the algebraic multiplicity mu sub A of lambda sub I specifies how many times it shows up as a root of the characteristic polynomial of A. This multiplicity is the highest integer k, for which the term lambda minus lambda sub I to the power of k divides the characteristic polynomial without leaving a remainder. For a matrix A with n rows and n columns, having d distinct eigenvalues, where d is less than or equal to n, the characteristic polynomial can be represented as the product of d factors. Each factor corresponds to a unique eigenvalue and is raised to the power equal to its algebraic multiplicity. The algebraic multiplicity of each eigenvalue ranges from 1 to n. The total algebraic multiplicity, denoted as m of A, is the sum of the individual algebraic multiplicities and equals n. An eigenvalue, denoted as lambda I, with an algebraic multiplicity of 1 is called a simple eigenvalue. If the algebraic multiplicity of lambda E is equal to its geometric multiplicity, then lambda E is known as a semi-simple eigenvalue. The set E is defined as the collection of vectors V that satisfy the equation, open parenthesis, a minus lambda times I, close parenthesis, times V equals 0. This set encompasses both the null space of the matrix, open parenthesis, a minus lambda times I, close parenthesis, and the eigenvectors of matrix A corresponding to the eigenvalue lambda. Therefore, E includes the 0 vector and all eigenvectors associated with lambda, making it equivalent to the null space of open parenthesis, a minus lambda times I, close parenthesis, and is referred to as the eigenspace or characteristic space of matrix A related to lambda. Since E is a linear subspace, it is closed under addition and scalar multiplication, reinforcing its stability. The dimension of the eigenspace, referred to as the geometric multiplicity of an eigenvalue, represents the highest number of linearly independent eigenvectors associated with a particular lambda. This multiplicity is calculated by taking the dimension of the matrix n and subtracting the rank of the matrix A minus lambda times the identity matrix. The geometric multiplicity for each eigenvalue must be at least 1, and it cannot be greater than its algebraic multiplicity, which in turn cannot exceed n. The formula for the geometric multiplicity is given by gamma sub A of lambda equals n minus the rank of the matrix AA minus lambda times the identity matrix. This formula highlights the critical relationship between eigenvalues, eigenvectors, geometric multiplicity, and algebraic multiplicity, providing insight into the properties of matrices within the framework of linear algebra. When a matrix A has d distinct eigenvalues, with each eigenvalue lambda sub I having a geometric multiplicity of gamma sub A of lambda sub I, the total geometric multiplicity gamma sub A is the sum of the geometric multiplicities of all eigenvalues. These values range between the number of distinct eigenvalues, d, and the size of the matrix, n. If gamma sub A is equal to n, then all the eigenspaces of A's eigenvalues together form the complete vector space C superscript n. A complete basis for C superscript n can be created using n linearly independent eigenvectors of A, known as an eigenbasis. Any vector within C superscript n can be expressed as a linear combination of A's eigenvectors. For any n by n matrix A with complex number eigenvalues denoted by lambda 1 to lambda n, each eigenvalue appears mu subscript A of lambda I times in the list, where mu subscript A of lambda I represents the algebraic multiplicity of that eigenvalue. Several properties can be attributed to this matrix and its eigenvalues. The trace of A, which is defined as the sum of its diagonal elements, is equivalent to the sum of all eigenvalues. The determinant of A is the product of all eigenvalues. The eigenvalues of the kth power of A, denoted as A raised to the power of k, are the kth powers of the individual eigenvalues of A. The matrix A is invertible only if all eigenvalues are non-zero. In the case of an invertible A, the eigenvalues of its inverse are the reciprocal values of the original eigenvalues. If matrix A is Hermitian, meaning A equals its conjugate transpose A star, or symmetric and real, then all eigenvalues of A are real. Additionally, if matrix A is Hermitian and satisfies the conditions of being positive definite, positive semi-definite, negative definite, or negative semi-definite, then all eigenvalues will be positive, non-negative, negative, or non-positive, respectively. In the case when matrix A is unitary, all eigenvalues have an absolute value of 1. If matrix A is an n by n matrix with eigenvalues denoted as lambda 1, lambda 2, up to lambda k, then the eigenvalues of matrix I plus A are lambda 1 plus 1, lambda 2 plus 1, up to lambda k plus 1. Furthermore, for any complex number alpha, the eigenvalues of matrix alpha I plus A are lambda 1 plus alpha, lambda 2 plus alpha, up to lambda k plus alpha. In a more general sense, if P is a polynomial, then the eigenvalues of the matrix P of A are P of lambda 1, P of lambda 2, up to P of lambda k. In many fields, vectors are often represented as column matrices instead of row matrices. When talking about matrices, the term eigenvector usually refers to a right eigenvector, which is a column vector used in the equation A times equals lambda times V, where A is an n by n matrix. Eigenvalues and eigenvectors can also be considered for row vectors that multiply the matrix A from the left. In this case, the equation U times A equals kappa times U, where kappa is a scalar and U is a 1 by n matrix, describes a left eigenvector of A that corresponds to its related eigenvalue kappa. By transposing this equation to A transpose times U transpose equals kappa times U transpose, it's clear that a left eigenvector of A is the same as the transpose of a right eigenvector of A transpose, with the same eigenvalue. Furthermore, since the characteristic polynomial of A transpose is the same as that of A, the eigenvalues for the left and right eigenvectors of A are the same. The process of diagonalization and eigendecomposition involves the assumption that the eigenvectors of a matrix A form a basis. This means that matrix A has n linearly independent eigenvectors, which we will denote as V1, V2, up to Vm. These eigenvectors correspond to eigenvalues, which we represent as lambda 1, lambda 2, through to lambda. It's important to note that these eigenvalues do not have to be different from one another. To achieve this transformation, we create a square matrix Q. The columns of this matrix Q are composed of the linearly independent eigenvectors of A. So we write Q equals the matrix with columns VB1, V2 through to Vn. Using this matrix Q, the original matrix A can be converted into a diagonal matrix, which we denote as capital lambda. In this diagonal matrix, each diagonal entry, denoted as lambda subscript 2, corresponds to the eigenvalue related to the ith column of the matrix Q. The equation at times Q equals Q times lambda allows us to express the matrix A as Q times lambda times the inverse of Q, or the inverse of Q times A times Q equals lambda. This describes the eigendecomposition in a type of similarity transformation. This transformation illustrates how matrices A and lambda represent the same linear transformation in different bases using eigenvectors. In the event that a matrix A is diagonalizable, a non-singular square matrix P enables the representation of A as some diagonal matrix D via the transformation P inverse times A times P equals D. Therefore, the eigenvectors of A form a basis if and only if A is diagonalizable. Matrices that cannot be diagonalized are termed defective and entail the concept of generalized eigenvectors and the Jordan normal form for their representation. In an algebraically closed field, any matrix has a Jordan normal form, allowing a basis of generalized eigenvectors and a decomposition into generalized eigenspaces. In linear algebra, particularly for Hermitian matrices, there is a way to characterize eigenvalues using variation. The largest eigenvalue of a matrix H can be determined by finding the maximum value of the expression formed by multiplying matrix H by vector x from both sides and dividing it by the product of vector x with itself. This can be written in symbols as x transpose hx divided by x transpose x. An eigenvector is a specific vector x that results in this maximum. For instance, consider a two-dimensional matrix A, which is given as follows. Matrix A is the following. First row contains the numbers 2 and 1. Second row contains the numbers 1 and 2. This matrix A maintains the direction of vectors that are parallel to its eigenvectors, meaning transformations applied by A do not alter these directions. However, vectors that are not parallel to the eigenvectors will be affected by the transformation. To find the eigenvalues of matrix A, one would determine the determinant of the matrix A subtracted by lambda times the identity matrix, often denoted as lambda I. Then, by solving for the roots of the resulting equation, the eigenvalues can be defined. For our specific matrix A, the eigenvalues turn out to be lambda equals 1 and lambda equals 3. These eigenvalues correspond to specific eigenvectors. Lambda equals 1 corresponds to the eigenvector with components 1 and minus 1, while lambda equals 3 corresponds to the eigenvector with components 1 and 1. In three-dimensional matrices such as matrix A, defined by the elements 2, 0, 0, 0, 3, 4, 0, 4, 9, the roots of the characteristic polynomial provide the three eigenvalues of the matrix A. Each eigenvalue is associated with specific eigenvectors. For instance, the vector 1, 0, 0 transposed, and the vector 0, negative 2, 1 transposed. In cases where complex eigenvalues arise, such as in matrices like matrix A with elements 0, 1, 0, 0, 0, 1, 1, 0, 0, these eigenvalues consist of both real and imaginary parts. This results in complex eigenvectors that appear in conjugate pairs. Diagonal matrices have entries only along the main diagonal, making them a unique type of matrix. For a specific matrix like matrix A, given as a 3 by 3 matrix with elements 1, 0, 0 in the first row, 0, 2, 0 in the second row, and 0, 0, 3 in the third row, the characteristic polynomial is calculated as the determinant of matrix A minus lambda times the identity matrix. This is expressed as the product of three factors, 1 minus lambda, 2 minus lambda, and 3 minus lambda. Solving this polynomial gives us the eigenvalues lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. These eigenvalues are exactly the diagonal elements of the matrix and represent the eigenvalues of matrix A. Each diagonal element corresponds to an eigenvector where the non-zero component is positioned in the row corresponding to the eigenvalue. For the example matrix, the eigenvectors are vector v sub lambda, 1 equals the vector, 1, 0, 0, vector v sub lambda, 2 equals the vector, 0, 1, 0, and vector v sub lambda, 3 equals the vector, 0, 0, 1. These eigenvectors are associated with their respective eigenvalues. We are discussing triangular matrices, which are classified into two types. Lower triangular matrices, where non-zero entries are below the main diagonal, and upper triangular matrices, where non-zero entries are above the main diagonal. For triangular matrices, the eigenvalues are located in their main diagonal elements. Consider the lower triangular matrix labeled as A. The elements of matrix A are arranged as follows. The first row is 1, 0, 0. The second row is 1, 2, 0. And the third row is 2, 3, 3. The characteristic polynomial of the matrix A, which is determinant of open parenthesis, A minus lambda, I close parenthesis, can be expressed as open parenthesis, 1 minus lambda, close parenthesis multiplied by open parenthesis, 2 minus lambda, close parenthesis, multiplied by open parenthesis, 3 minus lambda, close parenthesis. Solving this polynomial results in the eigenvalues being lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. These values are actually the main diagonal elements of the matrix. The eigenvalues are associated with the following eigenvectors. For lambda 1 equals 1, the eigenvector is open bracket 1, negative 1 over 2, close bracket. For lambda 2 equals 2, the eigenvector is open bracket 0, 1, negative 3, close bracket. For lambda 3 equals 3, the eigenvector is open bracket 0, 0, 1, close bracket. When dealing with a lower triangular matrix labeled A, with entries in a 4x4 grid as top row, 2, 0, 0, 0, second row, 1, 2, 0, 0, third row, 1, 3, 0, and fourth row, 1, 3. The characteristic polynomial for matrix A comes out to be given by open parenthesis, 2 minus lambda, close parenthesis, squared times open parenthesis, 3 minus lambda, close parenthesis, squared. The roots of this characteristic polynomial are 2 and 3, each appearing with an algebraic multiplicity of 2. The geometric multiplicity, which indicates the number of linearly independent eigenvectors associated with each eigenvalue, might differ from the algebraic multiplicity. In this scenario, the geometric multiplicity for eigenvalue 2 is 1, indicating there is one linearly independent eigenvector corresponding to this eigenvalue. Similarly, the geometric multiplicity for eigenvalue 3 is also 1. This yields a total geometric multiplicity of 2, aligning well with the fact that this matrix has two distinct eigenvalues. Moreover, an interesting identity arises when working with Hermitian matrices, which are a type of square matrix. The squared norm of a component of a normalized eigenvector can be calculated by using the matrix's eigenvalues along with the eigenvalues of the associated minor matrix. This concept is particularly useful, simplifying computations related to eigenvectors and eigenvalues in Hermitian settings. The definitions of eigenvalue and eigenvectors of a linear transformation remain applicable in the realm of infinite-dimensional Hilbert or Banach spaces. One common type of linear transformations in such spaces are differential operators that act on function spaces. For example, let's consider a linear differential operator denoted as D, operating on the space of infinitely differentiable real functions of a real variable t, called C infinity. The corresponding eigenvalue equation for D is given by d of f of t equals lambda times f of t. Functions that satisfy this equation are referred to as eigenvectors of D and are commonly known as eigenfunctions. To illustrate this, let's consider the derivative operator, expressed as d over dt, and the eigenvalue equation written as d over dt of ef of t equals lambda times ef of t. To solve this differential equation, we multiply both sides by dt over fe of t and then integrate. The solution to this equation is given by the exponential function f of t equals f of 0 times e ad the raised to the power of lambda times t. This solution serves as the eigenfunction of the derivative operator. It's important to note that in this case, the eigenfunction changes based on its associated eigenvalue. For example, if lambda equals 0, the eigenfunction f of t simplifies to a constant function. Other examples of eigenfunctions are discussed in the broader context. The concept of eigenvalues and eigenvectors applies to any linear transformations on vector spaces. Consider a vector space V over a field K of scalars and a linear transformation T that maps V to itself. A vector V in the vector space V is called an eigenvector of the transformation T if there exists a scalar lambda, L, in K such that applying the transformation T to vector V results in lambda times the vector V. This relationship can be described by the equation TV equals lambda V, which is referred to as the eigenvalue equation for the transformation T. Here, lambda is the eigenvalue associated with the eigenvector V. The eigenspace associated with an eigenvalue L is the set of all vectors VE for which TV equals LV. This eigenspace, denoted as E, comprises the 0 vector along with all eigenvectors related to L, forming a linear subspace of V. If the dimension of this subspace is 1, it is referred to as an eigenline. The geometric multiplicity Yerstanti L of an eigenvalue Alceo represents the dimension of the eigenspace associated with L, signifying the maximum number of linearly independent eigenvectors tied to that eigenvalue. Eigenspaces of T collectively form a direct sum, implying that eigenvectors linked to distinct eigenvalues are always linearly independent. Consequently, the total dimensions of the eigenspaces cannot surpass the dimension n of the vector space operated on by T, limiting the number of distinct eigenvalues to n at most. Any subspace spanned by T's eigenvectors is an invariant subspace of T, and T becomes diagonalizable when restricted to such a subspace. If V can be spanned by T's eigenvectors, or if the direct sum of eigenspaces related to all eigenvalues of T covers the entirety of V, an eigenbasis can be constructed from linearly independent eigenvectors, resulting in a diagonalizable T. If lambda is an eigenvalue of the operator T, then the operator T minus lambda times the identity operator does not create a one-to-one mapping, meaning it does not have an inverse. This holds true in finite-dimensional vector spaces, but it does not always apply to infinite-dimensional vector spaces. In the context of functional analysis, the concept of eigenvalues expands to the spectrum of a linear operator T. The spectrum comprises all scalar values, lambda for which T minus lambda times the identity operator does not have a bounded inverse. The spectrum of an operator inherently includes all eigenvalues, but transcends them. Introducing associative algebras and representation theory, the transition from a single operator acting on a vector space to an algebra representation acting on a module permits the exploration within representation theory. Weight, a pivotal notion in representation theory, mirrors eigenvalues, with weight vectors and weight spaces mirroring eigenvectors and eigenspaces correspondingly. Notably, the Hecke eigensheaf, a self-tensor product, is central to the Langlands correspondence. The classical method involves finding the eigenvalues first and then calculating the eigenvectors for each eigenvalue. This method, however, is not well suited for non-exact arithmetics like floating-point computations. Determining the eigenvalues of a matrix involves finding the roots of the characteristic polynomial. While this is straightforward for 2x2 matrices, it becomes significantly more challenging as the matrix size increases. The computation of coefficients for the characteristic polynomial is theoretically exact, but in practice, round-off errors contaminate the coefficients, making it unfeasible to find all roots of a polynomial with high accuracy. Explicit algebraic formulas for polynomial roots exist only for degrees up to 4, as per the Abel-Ruffini theorem, offering no general formula for degrees 5 or higher. Consequently, matrices of size 5 or greater require approximate numerical methods to compute eigenvalues and eigenvectors. Efficient and accurate methods for computing eigenvalues and eigenvectors of matrices emerged with the QR algorithm's development in 1961. The combination of Householder transformation with LU decomposition yielded an algorithm with superior convergence compared to the QR algorithm. For large Hermitian sparse matrices, the Lanczos algorithm stands as one of the efficient iterative methods to compute eigenvalues and eigenvectors, amidst other possibilities. Most numerical methods computing a matrix's eigenvalues also determine the corresponding eigenvectors during the process, although sometimes the eigenvector information is discarded once its utility is fulfilled. Geometric transformations involving eigenvectors and eigenvalues provide valuable insights into the linear modifications of geometric figures. Various transformations such as scaling, rotation, shearing, and hyperbolic rotation can be represented by 2x2 matrices with corresponding eigenvalues and eigenvectors. For instance, a rotation matrix written as open bracket cosine theta, negative sine theta, cosine theta, close bracket signifies a rotation by an angle of theta degrees, altering the direction of all non-zero vectors in the plane. Principal component analysis, PCA, utilizes eigendecomposition with symmetric positive semi-definite matrices to establish an orthogonal basis of eigenvectors and non-negative eigenvalues. This method is applied in multivariate analysis to examine sample covariance matrices, enabling dimensionality reduction in large datasets and identifying significant variance in data. In the domain of spectral graph theory, Eigenvalues and eigenvectors are crucial in characterizing graphs and their adjacency, or Laplacian matrices. The principal eigenvector, linked to the largest or smallest eigenvalue, serves to measure the centrality of graph vertices and has practical applications like Google's PageRank algorithm and spectral clustering for graph partitioning. Eigenvalues and eigenvectors play a vital role in various scientific fields, extending to mechanics, quantum mechanics, wave transport, molecular physics, geology, infectious disease modeling, and image processing. They aid in analyzing vibration modes, principal axes in rigid bodies, stress tensors in solid mechanics, solving nonlinear eigenvalue problems in quantum chemistry, and interpreting the basic reproduction number in epidemiology. Additionally, in image processing, eigenfaces and eigenvoices are utilized for facial and voice recognition, demonstrating the versatile applicability of eigenvectors and eigenvalues across different disciplines.